I'm ready. I hope you can hear me, and I'm happy to be here. I hope you're all doing well. I would like to present to you some insights from a campaign reanalysis reproduced based on a campaign that was happening in summer 2023 in the southwestern mountain ranges of Germany. And one special thing about this campaign was that we deployed a network of 12 Doppler wind lidars that have until then not been used for data assimilation experiments before. And since then, we are trying to evaluating this data set. And I would like to present you, but also like to discuss with you what we can learn from this data set. This work is in collaboration with people from IMK from the University of Karlsruhe, from the German Weather Service, University of Bologna, and also Meteo Swiss, who provided additional wind lidar data that you can see also here on the map on the left. Let me just, yes. Let me quickly introduce to you the campaign. The name is Swabian Moses 2023. As I said, it was conducted in the 3 summer months in 2023. And the goal was, among others, to learn more about the initiation of thunderstorms in this southwest German area and how this initiation process depends on mesoscale flow conditions. And I will only tell you a bit about the observations we used for assimilation. Of course, there were many more that were conducted, but for assimilation, we used 6 meteorological masts that you can see here as orange stars, in addition to the operational ones. There was an additional mobile X-band radar installed to the east of the Black Forest Mountains. Then we assimilated 2 additional sites with radio sounding launches, and actually a German-wide or domain-wide network of GNSS retrieved zenith total delays. And most of all, and that's the main subject of this talk today, this network of 12 Doppler wind lidars, from which first was retrieved vertical profiles of the horizontal wind components, which were then assimilated as observation type pilot. And if you now rearrange these observations in terms of the number over the 3 months and by assimilated variable, we immediately see that wind observations were the vast majority that we assimilated additionally to the operational ones from this campaign in that specific area. The area I'm talking about, I will call Black Forest domain, is the one inside this square. And here you can see again a bit more of the orography. And to put this a bit more into numbers, in this area, we assimilate in total 45% more observations than operationally for the campaign reanalysis. And that also means that in total, Doppler wind lidar observations make up 25% of all observations assimilated in the Black Forest area. Why did we do this in the first place? As was just already pointed out, there is this boundary layer observation gap. As we know, more and more satellites are assimilated, but we still lack measurements in the lower troposphere and especially the boundary layer. And for this, a network of Doppler wind lidars could potentially close parts of this gap, especially on the momentum side, and give us more information about the lower and mid-troposphere momentum distribution. And moreover, there are many studies that suggest that campaign observations can help to identify and reduce model biases, not only by a direct observation to model comparison or verification, but also via assimilation. And as I was already pointing out, this Swabian Moses campaign provides 3 months of high-resolution data from different observation systems, mainly of Doppler wind lidars in a region with moderately complex terrain, which is, I would say, even more interesting. And based on that, we thought that, or people thought that this data set should be used or can be used to evaluate if Doppler wind lidar observations can provide an added value to a numerical weather prediction model. And the one we're using here is the ICAN D2 model, which is the regional model of the German Weather Service. at 2.2 kilometer effective mesh size. First of all, it's added value on the analysis, and then hopefully in the future to see if there's an influence or a positive impact on the forecast. Let me give you a short overview of our assimilation experiment setup. The general idea was to stick as close as possible to the operational forecasting chain of the German Weather Service. And as I already told you, we used the icon model, in this case on the D2 domain, which is centered over Germany, but also includes the neighboring countries and has then an effective mesh size of 2.2 kilometers. And in that case, convection is permitting, and only shallow convection is parameterized. And this one is then coupled to the kilometer scale ensemble data simulation system Keller, which employs an LETKF. And here, as I was saying, we mainly copied the values that are used for the operationally assimilated observations. So for example, for the Doppler wind lidars, which are assimilated as observation type pilot, we use the same default observation errors as are, for example, used for radar wind profilers. Same holds for localization. Of course, if it's adaptive, it's not constant, but we didn't so far make any changes to it. And yeah, I have to say these experiments have been set up and computed by our colleagues from DWD, mainly Gernot, Hendrik, and Thorsten. I've seen you in the audience, so thank you again very, very much. And with this, we did a 3-month continuous cycling with a 1-hour assimilation forecast step, which gives us in the end about 2,000 time steps to evaluate. Okay, and of course, we did not only do this campaign reanalysis, but also a control reanalysis, where we basically have the exactly same setup, but denying the campaign observations. And from now on, I will mainly compare this campaign reanalysis with the control reanalysis. And there are some questions I would like to address and answer. And the first one is how, in general, do the additional Doppler wind lidar observations, or all the observations from the campaign, but mainly Doppler wind lidar observations, influence the campaign analysis, and how does this compare to the control? And what you can see here is, first of all, in this panel A, the mean wind speed and wind direction over the course of these 3 months. So that's a composite, just to illustrate to you that the main prevailing wind direction was southwesterly. And you do see the effect of the orography, but keep in mind that the Black Forest is quite a medium to low range mountain range, and this kind of gravity or orography effect that you can see in this panel B is also due to the squeezing of this cross section. Yeah. So what I would like you to look at next is this panel C and D, where you can see in colored shading the mean absolute increment or difference in increment, which gives us mainly the absolute influence of the campaign observation in addition to the control. And this nicely correlates, and it's meant to be like this, with the mean difference and with the mean increment, and you could shown by the arrows, and you can already see that these kind of point opposite to the mean wind direction. And then the shape of this mean absolute increment also correlates with the shape of the localization weights that were used for the Doppler wind lidars. So this is mainly a sanity check, but it already shows you that the observations from the campaign do have a substantial influence on the campaign reanalysis compared to the control. And then in the lower panel in G and H, you can see kind of the accumulated effect through the cycling, because here we look at in colors, the mean absolute difference between the campaign and the control analysis, which gives us a similar shape, but with much higher values. And we can also see that this accumulated effect of always reducing the wind speed via these increments gives us a strongly reduced wind speed in the campaign compared to the controlled reanalysis. Okay. In addition, what I would like to show you is some work that my colleague Maurus has done based on the partial analysis increment method developed by Teresa Diefenbach, who I've also already seen in the audience. And this method is used to approximate the influence of individual observations, or if you then again sum up these partial analysis increments, you can identify the influence of individual observation types. And in our case, Maurus evaluated what is the relative impact of the Doppler wind lidar observations from the campaign, which is here in orange and this dashed shades, relative to all the others. So they all sum up to 100%. And you can see that the Doppler wind lidars contribute, for example, at 700 hectopascal, about 60% to the total increment. And it's a similar picture you can see for the meridional wind, just with an influence even higher up. And we'll come back to this also later in the talk. And interestingly, we not only see an influence on the zonal and meridional wind component, which of course is expected and wished, but we also see an influence on temperature and humidity. If you have questions regarding this, I can try to answer these, but I'm not an expert, then you would have to contact Maurus in the meantime. And then we'll come to the second question I would like to answer to you during this result part, which is there a systematic influence of the additional Doppler wind lidar observations on the campaign analysis? And if so, when and where would we find these systematic influence? And for this, we first look again at mean fields, but we look at only those time steps where we had westerly flow conditions to kind of separate westerly from easterly regime. We looked at many different ways of stratification. We found out that this is gives us the most, let's say, biggest difference between regimes, or significant difference. And this is also the case in 85% of all time steps, so the vast majority of these 3 months. And you will again see the mean difference between the campaign analysis and the control reanalysis. First, we look at the difference in the zonal wind component at 1.5 kilometer above sea level. And you've already seen it in with these arrows before. Here, the campaign reanalysis is systematically slower than the control. And if we go higher up, we still see this signature, but much less pronounced, which with much lower values. On the other hand, if we look at the meridional wind component, which you can see here, we don't see such a clear signal or clear shape in the low levels, but if we go up to 4 kilometers above sea level, there's a very systematic increase of the meridional wind component in the campaign reanalysis compared to the control. So here we see kind of different signs of this difference, also at different heights. And to complete this kind of three-dimensional picture, I would like to give you, we can also look at a vertical cross-section on this regarding this mean. And here we again see that the increase, the faster meridional wind due to the increments based on the Doppler wind lidars, we see higher up for the meridional component, and this reduction of zonal wind we see rather below 3 kilometers or so. And we've been looking at this a lot, but we don't have a let's say, clear physical explanation of why this happens yet. In addition, we can, of course, also look at the easterly regime, and to complete the picture again, this is now evaluated based on bind data, but also increments from the campaign analysis. We see again what I have just been showing to you. So the meridional component is faster in the campaign reanalysis than in the control, rather higher up. The zonal component is slower in the campaign than in the control, and rather in the lower levels. And in total, that gives us a reduction or a slower wind speed in the campaign than in the control reanalysis, mostly during daytime. And if we do the same for the easterly regime, which of course has a much slower or lower sample, so it's not as clear, we see that here really the diurnal cycle plays a role, and we have generally higher absolute values during the day, but the sign of the increment is different during the day versus during the night. So this looks more like an effect of the boundary layer growth, because of course these easterly days are more in anticyclonic conditions. And then the third question I would like to address is, how does this observation influence? Is it maintained in the forecast, or does the free forecast directly remove the influence of the campaign observations, or does it enhance the systematic differences that I've just been showing to you? And for this, I would like you to just first have a look on the left side. Here we see for 1 week of example forecasts we've been computing initialized from the campaign from the campaign reanalysis, but also from the control. 12-hour lead time forecast initialized at 0 UTC. So the x-axis is the nominal time, but also the lead time. And you see a median diurnal cycle. So this is not one forecast. This is always the median of these 7 days. And the dashed blue is the campaign analysis. And you can immediately see that all the other 3 lines lie much closer together than the campaign analysis. So here it looks like, but again, I would like to stress that this is just from 1 week sample, that the increment, or that the analysis cannot, let's say, balance to this new state, but quickly relaxes back to the control state, and then is much more similar to the control reanalysis. And the picture is kind of similar in the meridional component, but again, none of this is significant, and we would need a larger sample to make some statistical statement here. And on the right, you can see that in general, the difference between the forecast and the analysis is also larger. So that underlies what I was just saying, that the forecast based on the campaign reanalysis is much faster relaxing back to the model balanced state, or of the forecast balanced state, than it does in the control. Probably due to time constraints, or can someone tell me if I still have a minute?
Meanwhile, you are muted.
I would say probably it's best for you to finish this presentation.
Okay, yeah, I didn't
we'll leave
hear
the
2-minute call.
notes.
Okay. Because then I finish here. If you have any questions on the forecast, just contact me in the aftermath. So I've been showing you that that the Doppler wind lidars do influence the analysis wind field, not only in the campaign area, but via the cycling also beyond. That they also have an influence on the thermodynamics of the model of the analysis state. Then in addition, we see that the Doppler wind lidar increments systematically change the analysis field, which leads to an anti-clockwise rotation of the wind and a slightly slower wind speed in the lower levels above the domain, and that we do see that this additional information is not maintained very long in the forecast, but to make a really clear statement on that, we would like to have more reforecasts, and we're currently busy with doing this. And with this, thanks for your attention.
All right. Thank you, Julia, for the excellent talk. I don't think we have time for questions for now, but please submit your questions using the UPad link provided, and Julia may answer your questions from the online document during the rest of the meetings. Thanks again, Julia.